Okay, so the next speaker is Rajeev Jain that will tell us about primordial black holes from inflation. Whenever you are done, please go.
Thanks. Can you hear me at the back? All right. All right, so good morning, everyone. Before I start, let me thank the organizers for the kind invitation. Of course, as you can see, I'm based in Bangalore, just 20 kilometers away from ICTS. So I plan to talk about a bunch of pieces of work that we have been doing on understanding the generation of primordial black holes from inflation. And I'll be talking about a bunch of different observational imprints in terms of dark matter, the secondary gravitational waves, and also some imprints from Hawking evaporation. And this is contrary to what Ma talked about just now. So we'll be talking about the cold inflation scenario, the usual cold inflation scenario, while Ma was talking about the warm inflation scenario. And this talk is going to be based on a bunch of papers over the last couple of years. And most of this work was part of the thesis of my first student who was around, but he's not around anymore. And then we have been also carrying out some more work along the direction of understanding various imprints, new probes to constrain the overall dynamics of and formation aspects of primordial black holes. So I believe whatever I'm going to talk about, many of the things you may have heard already in this meeting, but I'm sure there will be some new stuff that you would find interesting. All right, so so the plan of the talk is as follows. I'll start with a very general question that many of you know. Why do we need to talk about primordial black holes? And needless to mention, these are one of the very interesting probes of the small scale dynamics during inflation. Okay, and I'll make a few remarks as I go along. I'll quickly jump to the generation mechanisms of primordial black holes, and in particular, I will focus on mechanisms during inflation, in particular during single field inflation, some models that we have looked at, which we found to be very interesting. I mean, not just us, many other people have looked at on these so-called the inflection point single field inflationary models. I'll talk about how to compute the PBH mass fraction in these models. And of course, I will briefly comment about that any quantity of physical relevance that you compute is going to be highly model dependent. Okay, so it's very difficult to say anything in general about model independent results in the context of PBH formation. And then I will move on to some of the interesting imprints of PBH. The idea essentially is to use various different tools, various different observables to constrain the formation aspects of primordial black holes from inflation. In particular, I will go through one by one through the secondary gravitational waves that Mar has talked about, at least the basic formalism, and many other people have talked about in this meeting. Imprints from Hawking evaporation. If we assume that any black hole, in particular the PBH, are supposed to evaporate, there are going to be a bunch of different interesting imprints from the evaporation. And then whether you can also reconcile the induced GW from some of these scenarios and whether you find them to be consistent with the PTA results, something that has been of interest lately. And towards the end, if time permits, I'll also talk about one of our recent work. What are the imprints of the memory burden effect onto the stochastic GW background, and then I will conclude. All right. All right, I don't think I need to go through this slide. Everybody is aware of this. So-called the standard model of cosmology or the concordance model. The universe consists of radiation, baryons, dark matter, and dark energy. And we usually describe it with the FLRW background, which means you think of the universe being statistically homogeneous and isotropic on very, very large scales. And this goes by the name of lambda CDM model. And as you can see that we only understand 5% of it, okay? The remaining 95% we don't understand, namely the dark matter and dark energy. In my opinion, dark energy is a bit more exotic component. Dark matter is something we can try to understand. And that's what we do. We try to understand dark matter. And of course, we have a lot of observational evidence for the presence of dark matter. Okay, we don't know what it is, but we know that it does exist, okay? Observation from the galaxy rotation curves, observation from bullet cluster, and of course, a very direct evidence from the cosmic microwave background. In order to fit these acoustic peaks, you need to have a certain fraction of dark matter energy density. And therefore, we have a lot of evidence for the presence of dark matter across the universe at different length scales. However, as I said that, we just don't know what it is, okay? So we know it exists, we just don't know what it is, so it's definitely one of the known unknowns among the many known unknowns in the universe, okay? And of course, people have been working on various candidates of dark matter, okay? I don't want to get into any of these. I just want to emphasize upon the fact that in addition to dark matter being a microscopic particle, one can also think of dark matter being a macroscopic object, okay? A macroscopic particle, and the candidates which have been proposed, if you look at this side of this, this picture, machos, primordial black holes, and many other objects would fall in this category. Okay, there are tons of constraints on the existence of any of these, and I will talk about some of them. So PBH, which is sort of mentioned here, are one of such candidates that if you produce them abundantly in the early universe, they can behave. And if they do not evaporate completely by means of Hawking evaporation, they can be one of the novel candidates for the dark matter today. Okay, and I'm going to discuss about how you can abundantly produce them in the sense of having the right fraction of energy density that we need today. Interestingly, these PBH are non-baryonic, they are non-relativistic and nearly collisionless. Okay, and of course, you don't really need any exotic physics to produce them. Okay, as I will discuss, you need something beyond the conventional idea of slow inflation, but you still don't need any exotic physics to produce them. And as I mentioned briefly earlier, if you produce them, you do not have them as a candidate for dark matter. They can also induce a bunch of other signatures, for instance, the secondary gravitational waves or imprints from Hawking evaporation. And these provide you additional novel tools to constrain the dynamics of the PBH protection, let's say during inflation. All right. So this is again a plot that all of you would have seen, perhaps. What I'm plotting is the fractional energy density in the PBH with respect to dark matter as a function of mass. And there are going to be various constraints from, lensing, micro-lensing, and, various other things, CMB, and even the Hawking evaporation, okay? Forget this little hill over here, which has disappeared by now. What you find is that this plot essentially tells you that you can have primordial black holes as dark matter in this particular interesting mass range for about 3 to 4 orders of magnitude, which correspond to so-called the asteroid mass range. Therefore, the aim of everybody or anybody and everybody who is interested in building models of inflation to be able to produce primordial black holes enough in this mass range such that they don't suffer the evaporation constraint and they can still be a candidate for the dark matter, cold dark matter today. Okay, so this is a very simple version of this plot. If you want to look at a very sort of busy version of this plot, you come to this. Okay, and once again, the message is the same, that in this asteroid mass range, you essentially can produce, or you can have PBH as the entire dark matter. Okay, they are the usual, the constraints from Subaru and Ogle and many other things, and extending to even higher mass ranges. Okay, many of them being mentioned here. And we wrote a comprehensive review on PBH aspects and their gravitational wave signatures in 2023 as a part of the LISA Cosmology Working Group. And if you're interested, I would urge you to look at this, this paper or this review article, which is going to appear in the Living Reviews shortly. This really is a comprehensive review of not only the generation aspects of PBH, but many other observational imprints, as well as new tools to constrain the fraction and the dynamics in the early universe. All right, so let's move to how one can produce PBH during inflation. And the idea is not too difficult, it's rather simple. So you already know that length scales leave the horizon during inflation, okay? And in the simplest slow roll inflationary scenarios, they remain frozen outside the horizon, and then they re-enter the horizon at later epochs. All right, so you can think of these length scales being, co-moving length scales being constant, okay, two different length scales. This is a larger length scale, the blue line, and the green line being a smaller length scale, all right? And you are comparing this with respect to the horizon, okay? And as I said that these are the large scales, sort of which leave the horizon early on during inflation, and then they are nearly frozen and they re-enter again, all right, at later epochs. So the larger scales leave early and re-enter late. The smaller scales leave late and re-enter early, okay? They leave late and re-enter early. And on large scales, we of course have very tight constraints from CMB in terms of the power spectrum, namely that the power spectrum is nearly scale invariant with a given amplitude, but this only corresponds to the large scales, okay? If you think of inflation going on for about 60 e-folds, from CMB observations, you can at most constrain about 8 to 10 e-folds of inflation, not more than that. And of course, if inflation is supposed to last for 50, 60 e-folds, there's a whole lot of scales which do leave the horizon during inflation and re-enter later on. So from CMB, we just cannot say anything about the dynamics of these small scales during inflation, okay? There can perhaps be a very non-trivial dynamics happening later on, which could, lead to very different signatures in the power spectrum as compared to a nearly scale invariant power spectrum, which is essentially an outcome of slow roll inflation. Okay, so this is the idea that has been utilized in the sense that if there's a mechanism, if there's a dynamical mechanism, which could perhaps enhance the power spectrum on the smaller scales during inflation, when these scales with the larger enhanced power spectrum re-enter the horizon, they could collapse and form PBH. Okay, and then PBH can evolve further later on, but that is the aspect we will not be talking about in this talk. All right. So just to understand the same picture in a slightly different way, you compare the over densities with the size of the horizon, okay, at any given time, and only when these scales re-enter the horizon, and then if they have sufficiently large over densities, these are the regions which are going to collapse and form PBH, and typically we assume an instantaneous collapse and the formation of PBH during radiation domination in the simplest situations. And of course, one can understand that the larger over densities would collapse and form more massive black holes, and the smaller over densities would collapse and form smaller mass black holes. But all these over densities must be larger than something called the critical over density to form PBH. Okay, so this is a rough, naive, crude picture one has in mind as far as the formation of PBH during radiation domination is concerned. Okay, so what one is interested in, as I said already, is that the large scales are fairly well constrained with the CMB observations, with an amplitude of the co-moving curvature perturbations around 10 power minus 5 or so, and the spectrum being nearly scale invariant. And then, as I already said, that the CMB observations can only probe the 8 or 10 e-folds of inflation. However, the remaining, 40 to 50 e-folds of inflation, as far as CMB is concerned, CMB temperature and isotropies are concerned, remain largely unconstrained. So that's where the PBH formation at these smaller scales come into picture. Not only that, if they are produced in the right abundance, they can be a candidate for the cold dark matter. But in addition, they are one of the novel probe of these small scale dynamics during inflation. So just to understand this again very roughly before I go into a particular model, you can think of an inflection point model where you have a local plateau region in addition to a large scale nearly flat region which corresponds to the CMB scales, and eventually a global minima in which the inflaton field will roll down and end inflation. So you can think of this initial plateau region corresponds to the CMB scales, giving rise to nearly scale invariant power spectrum. The plateau region at some scales will lead to violation of these slow roll conditions, namely the evolution will go into the ultra slow roll regime, which is very crucial for producing PBH. And the final slow roll phase essentially will correspond to the end of inflation. Again, very crudely, you can understand what will happen around this region. If the so you think of the power spectrum as the ratio of h squared to epsilon. Okay, that's what you compute in slow roll. Again, this is not exact, just to give you an idea what could perhaps happen during this epoch. And epsilon, because the inflecton field slows down considerably, epsilon will become smaller and smaller as compared to this epoch. And as a result, you can think of, again, naively, an enhancement in the power spectrum of fluctuations around this epoch whenever epsilon becomes smaller considerably. So we looked at a particular model, and I just wanted to emphasize that there have been many people who have looked at these kind of models. The idea essentially, at least within the single field inflationary context, the idea essentially is to go away from the conventional slow roll dynamics, because this is what you need. In fact, you can think of this as a necessary condition to produce PBH, that you have to go away from conventional slow roll regime. And we looked at a particular inflection point model having certain, expansion in the field up to some order. And you find that if you take the large field or the small field limit, the potential is like quadratic. Okay, but you also realize that in any of these models, you need to compute the power spectrum or any prediction numerically. Okay, the analytical approximations are just not enough. Although in some case, one can try to work out analytical results, and they also match very well with the observations. All right. So one may naively think that it's x to the power 6, which is really high power, and as a result, this model could be ruled out. But as I said already, that in the large field regime, the potential still behaves as quadratic, and also there's even the quadratic model of inflation phi square is almost ruled out, as you perhaps know. However, we found that by doing it numerically as well as doing some analytical calculations, we found that it's not so much the case that just by looking at this, you can already assume or you can already conclude that this model is ruled out from CMB. We found that the tensor to scalar ratio, for instance, is still around 10 power minus 2 around the CMB scales. Okay, and this still makes this model just at the boundary of perhaps being ruled out, but it is not completely ruled out. But this feature around smaller field values, which essentially is a departure from slow roll, gives rise to a righteous abundance of primordial black holes. So I will not go into the details of all this. Again, I assume that all of you would have seen this is the background dynamics given by the Friedmann equations, the perturbation equations. This is how you compute the power spectrum. And again, as I said, you go dynamically from a slow roll to an ultra slow roll phase in these kind of models. Okay. Again, you can plot these slow roll parameters and look at the deviation, okay, for a few E-fold during this regime when the departure from slow roll to ultra slow roll takes place. And this is the regime which is crucial to produce essentially for the growth of primordial perturbations, which as a result will produce primordial black holes. So this is what you find. You take that model, you compute the power spectrum numerically, and this is what you find. For different choice of these inflection point, because the spectrum on the large scale is going to be sensitive, somewhat sensitive to the location of the inflection point. And this is something very generic, okay? We found that the large scales are not completely uncorrelated with the dynamics on the smaller scales, at least in these class of models. Which is again something very generic we found in the literature.
Rajeev, can I make 2 quick comments on this? Because there was a question when Jen Massimo was giving his lectures, because it would usually naively seem that CMB scale is separated from, but here is an example where you can see NS is pushed all the way to 0.9.
It's not completely separated.
Exactly.
There's a slight marginal dependence of what is happening and what scales on the smaller scales. It is going to affect somewhat, the larger scales as well.
And it's not just your model, but any inflection point.
Yes, we found that any single field inflection point model of inflation, this is a very generic feature.
Thanks.
In your scenario,
in my model, it works.
Yeah, it is or it is not?
It works.
Okay. Right, so there's a slight dependence, and there's something you need to worry about. As I said, that your large scale spectra corresponding to the CMB scale is already well constrained. Okay. The tilt is like 0.963, and this is something you cannot violate. These are the constraints you cannot violate. Not just the tilt, you also need to have the right amplitude of the spectrum. So just to summarize this plot is that all these scales corresponding to CME scales are well constrained from the Planck observations or any of the previous CME observations. And there's a non-trivial dynamics happening on the smaller scales because you sort of shift the location of the inflection point, which is also expected. Okay? At what epoch does the ultra slow roll come into picture is going to affect the enhancement of the primordial power spectrum. All right, so the solid lines are the primordial spectrum of co-moving curvature perturbations. The dashed dotted lines are the spectra for the gravitational waves, primordial gravitational waves, which is not so much affected. It is just affected because there is a change in the Hubble parameter during the ultra slow roll phase. So you take that and you plug it into your usual PBH recipe, which is essentially taking the power spectrum, you impose or you implement one of the formalism, collapse formalism, Peake's theory or Spreck-Schechter up to your taste, and you find out what is the fraction of PBH which is going to be there in a particular model. Okay, so I won't go into the details of this. I'm sure this has been covered already somewhere. And this is what you find. So given that power spectrum I just showed you, you compute this fraction, okay, and this peak in the power spectrum corresponds to different mass ranges, again for different choices of these inflection point, and you find that the value of NS differing significantly. Okay, that's the point I already emphasized. Okay, so for example, you can think of many of these values already being ruled out. So what we concluded in this model very strongly, that if you really want to produce PBH in this model, you cannot produce them in any mass range, because this is in somewhat tension with the NS constraint that you have on the large scales from CMB.
Can I make a positive comment?
Sure.
Since I made a negative one. So, but this is assuming your N star is in between 50 and 60. But
yes,
if your reheating history
it's a
is
large field model of inflation, okay.
But your reheating history might be different, because of which NS might be pushed to a different location where it
yeah, we found that there's a somewhat rather weaker dependence on the number of E-folds. So if you vary the number of E-folds, this might change, but I'm sure that you cannot bring this 0.90, the last one, to 0.963. That is just not possible. So we made a rather strong comment in the paper that many of these parameter space could actually are ruled out. Okay, which means you can't produce PBH in any given mass. You don't have that freedom to produce PBH in any mass range in this particular model.
We came up with the other model.
I'm well aware of it. So rather than a slow roll or ultra slow roll phase, one can also think of a slight deviation from the canonical power law in the potential model that Stochastic has worked on. And of course, each and every model, as I mentioned in the beginning, could lead to very different predictions, but there could also be parameter dependencies, strong parameter dependencies when you compute any of these quantities of interest. Okay, so every model, in my opinion, suffers from so-called the fine-tuning, as simple as that. All right, so we quickly looked at the effects of reheating. So initially I said that, you just think of PBH being produced during the radiation domination, when these scales are re-entering the horizon during radiation. But what we also found is that if you have a non-trivial reheating history after the end of inflation, in the sense that the universe doesn't go immediately into the radiation dominated epoch, you can affect this primordial spectrum as well as the abundance, essentially because of the remapping of scales between the exit and the entry. Remember, you compute the mass of PBH when a scale re-enter the horizon, and barring an efficiency factor, it is nothing but the mass of horizon at that epoch. So in the case of a non-trivial reheating history, which is, these other dashed and dotted lines, you essentially remap the exit and entry of scales, and as a result, this is going to imprint upon any quantity that you calculate. And this is what we found. There's a slight shift in the power spectrum, and as a result, there's a slight shift in the abundance, just modeling the reheating as, in terms of the duration and the equation of state during that epoch. All right? Fine, so let me move on quickly and come to the secondish part of the talk, where I start talking about these different observational imprints. So because Maya already covered this stochastic GW generation aspect, I will be quick with that. So I don't need to go through it. I'm sure everybody knows what is being written here, although it looks a bit complicated. So you can think of essentially, second order effects producing a secondary background of gravitational waves in addition to the so-called the primordial background coming from quantum fluctuations. And you are interested in looking at the power spectrum of these induced gravitational waves and see whether you can they can fall in the reach of the future gravitational wave observatories. So I won't go too much into detail due to lack of time. Okay, this is something you are aware of. So before showing you the outcome of this particular model, of course, you can think of an interesting connection amongst the peaks in the power spectrum that I had showed you in one of the plots to the peak in the abundance of PBH. And this is also going to be connected to the peak where the gravitational wave spectrum is peaked at. Okay? And there's a very interesting relation among the mass, the wave number at which the power spectrum is peaked, and the frequency at which the omega GW is peaked. Okay, so you can think of a PBH which is around 10 power minus 12 solar masses. This is going to give you a frequency which falls right at the millihertz frequency range, and as a result, LISA is going to be very sensitive to these kind of to the induced stochastic GW, which are produced from a PBH with 10 power minus 12 solar masses. And this is what we find, again, doing everything numerically, all those complicated two-dimensional convolution integrals numerically, this is what we find. So we find these peaked power spectra of the induced gravitational wave background corresponds to the peaked structure in the primordial power spectrum that I had shown you earlier. And you can see it corresponding to the different same set of parameters, essentially the different values of the inflection point. And you find that many of these predictions of this particular model could be constrained or detected with respect to the future gravitational wave observatories. Okay, so let me be a bit quick because of the short of time. And although we computed this numerically, there were also analytical or semi-analytical estimates to essentially compute the slope of this power spectrum. Okay, and this is given by a very nice IR scaling worked out in these two set of papers. And later on, it was also found that in addition to the frequency cube scaling, there's also a subdominant log correction. And the lines that we have plotted actually are with the log part. And you can see that they fit really nicely with the exact numerical spectrum. So the spectrum is not just coming out of black box. There's a very nice understanding of what you find numerically with what you find analytically. All right, again, the effects of reheating we explored a bit in this paper from 2021. And again, there's going to be some non-trivial effect on the GW background. In particular, what we found is that if you take the reheating being meta-dominated and lasting for long enough duration. So if you look at this brown sort of curve, in which the W reheating, as I said, that we are just naively modeling the reheating phase in terms of these two parameters, the number of E folds during reheating and the equilibrium state during reheating. All right. So if you take the brown curve, this corresponds to the W equal to 0, which means the meta-dominated reheating. And for sufficiently long E folds, you find that in addition to the primary peak, there's also a secondary peak. Okay. And this essentially corresponds to, we have worked out in this paper, essentially corresponds to the non-trivial evolution of these modes, which are re-entering during meta-domination, contrary to the radiation domination. And therefore, one has to worry about the non-trivial evolution of the transfer function, which goes into the calculation of omega GW. And you find that there's an interesting enhancement on rather higher frequencies in these kind of scenarios. And so that's where we stand in the sense of constraints on smaller scales. The large scales are very well constrained from CMB. There are constraints from mu distortions on somewhat smaller scales than the CMB. And then there are projected / derived constraints on this much smaller scales from SKA, LISA, ET, and also PBH. So any power spectrum that you have in mind, this is a power spectrum as function of wave numbers, any power spectrum that you work with cannot violate any of these constraints. For instance, you cannot violate the constraint of PBH because it will simply overproduce PBH, which means the energy density fraction would be larger than unity. So let me be a bit quick. Again, later on, we sort of looked at the aspect that rather than the PBH, which are candidate for the cold dark matter, which means they are massive enough, which means they don't completely evaporate by today. If you have these ultralight PBH, all right, such that they don't of course exist until today, but they evaporate by BBN, okay? And these are the black holes which fall, who has mass around 10 power 9, 10 power 10 grams. Keep in mind that the Hawking evaporation bound, which I showed in one of the plots, was around 10 power minus 17 grams, okay? Now what I'm talking about is ultralight PBH, which are around 10 power 10, 10 power 9, 10 power 10 grams. All right, so this is what I had shown you earlier. But if you try to see, if you ask the question, are there any constraints if you go further on this side? Just keep in mind that here the mass is plotted in terms of the solar mass being 10 power 33 grams. Here I'm plotting the, not me, but from this paper, the mass is plotted in terms of grams. And what you find is that even on these smaller mass range, which are on the left side of the Hawking evaporation cutoff bound, there are interesting constraints on the mass fraction of PBH. But in particular, you also notice that if you take this BBN, if you go to the left side of this around 10 power 10, even BBN cannot constrain these PBH, which means that these PBH are supposed to be completely evaporated by BBN, and as a result, BBN cannot constrain them. So the question we asked is that, is there any way you can still constrain the PBH with this particular mass range, because they completely evaporate by BBN. So we looked at the evaporation of these ultralight PBH, essentially, as I said, 10 power 9, 10 power 10 gram, and for these two different cases. So I'm sure many of these things you would have seen again. The temperature is just nothing but 1 over m for a PBH, and you can compute it. This is the lifetime of PBH evaporation. If the PBH are spinning, you have a correction coming from the angular momentum or the spin parameter, and that's how it is affected. Okay, you can think of the mass rate loss and the angular momentum loss in terms of these equations. And what people typically do is that, because these are these look simple, but they are non-trivial equations to solve. So people often switch to this publicly available code called Black Hawk. And what one is interested in is that what are the imprints one can look at, evaporation imprints one can look at for a given initial mass of PBH, okay, both for a spinning and non-spinning black hole. So we were in particular interested in a situation when these ultralight PBH, before being completely evaporate, they could dominate the universe for a brief period. So this is the typical picture that we had in mind, in the sense that after the end of inflation, the universe goes into an early radiation dominated epoch, okay, which is depicted by this red line. However, the PBH are still present, ultra low mass PBH. They come to dominate because the energy density scaling of PBH is different than radiation, and as a result, they come to dominate, okay. This epoch is going to give you a meta-domination, but of course, this is meta-domination before the usual meta-domination epoch, so we call this the EMD, the early meta-dominated epoch. These PBH at this particular epoch evaporate completely, and as a result of that evaporation, you again go into the radiation domination, and eventually you go into the conventional meta-domination. So the history of the universe from the end of inflation until the onset of radiation, until the onset of meta-domination, is slightly modified because of the presence of these ultra-low mass PBH and because of their evaporation. And we asked the question whether there are some imprints that you can look at from this kind of a scenario. All right, I'll be very quick. So in terms of energy density, you can think of, radiation being dominant. At some point, the PBH become dominant. And as soon as the PBH evaporate completely, you again go back to the radiation domination. All right, I'll be very quick with this part. So this has been worked out that when you have a distribution of PBH, in addition to the usual adiabatic perturbations that you have from inflation, you also have the isocurvature fluctuations arising from the distribution of PBH, okay? If you assume a Poisson distribution of PBH, one can work out the power spectrum of PBH fluctuations, the isocurvature fluctuations, with a cutoff given by the evaporation scale, okay? So just to summarize this part, that you would now have in these scenarios two contributions, okay, to the potential or to the power spectrum, one arising from your adiabatic inflationary perturbations that you have produced from inflation, and in addition to that, you will also have contribution arising from these isocurvature fluctuations from the PBH distribution, which will eventually be converted to adiabatic fluctuations, okay? So in these scenarios, you need to, when you want to compute the induced GW background, you need to worry about this component. And this is what we did. So we found that in addition to the conventional peak that you have from the adiabatic fluctuations, you also have a secondary peak arising from this secondary isocurvature perturbation contribution in these scenarios. And we also looked at the two cases when you have completely non-spinning black holes and maximally spinning black holes. And at least as far as this doubly peaked structure of GWs, induced GWs are concerned, we didn't find much of a difference. And then one can also look at the evaporation in terms of the contribution to the total number of effective number of degrees of freedom, and ask the question that if you have different species as an outcome of PBH evaporation for both these spinning and non-spinning black holes, whether you can constrain them or detect them with the future CMB observations. And we found that CMB HD or CMB Bharat is going to be an initiative from the Indian cosmology community for a CMB polarization experiment, can in principle detect and constrain the contribution arising from the evaporation. So I need to be quick. I will skip some of these things. If you have questions, we can talk later. So then we looked at whether these scenarios, when you have these ultra low mass PBH, can also explain the PTA signal. So we had this very interesting sort of signal from the PTA observations. And again, I believe Gopu must have covered some of these aspects, that there was a strong indication of a stochastic GW background from the PTA collaboration, okay? And this particular plot corresponds to the Hellingstown curve, which essentially tells you that this background must be stochastic. And then the collaboration itself in these papers, they looked at what kind of scenario can fit this signal, and they already looked at a bunch of these possibilities: induced gravitational wave background, and then secondary background from a delta function power spectrum, phase transitions from bubble collisions, and many other things. And they already found out that this conventional model, which is essentially based on the supermassive black hole binaries, is not so efficient to explain this signal. And as a result, many of these alternatives provide a better fit in terms of Bayesian evidence to the signal arising from NANO-Grav and other PTA measurements. So we looked at it and we found that if you have this peaked spectrum, okay, with a nearly scale invariant spectrum on the CMB scales, but a peaked spectrum around the PTA scales, you can find out using the same methodology that I discussed earlier, you find that you can actually explain the NANO-Grav signal in this particular scenario. And we also found that the Bayesian evidence was significantly larger than the reference model, which relies on the supermassive black hole binaries. Okay, I'll skip this. Very quickly, in the last 2-3 minutes, I'll quickly discuss one of our recent work on understanding the imprint of memory burden effect onto the PBH evaporation and any of the signals that I have talked about in terms of stochastic GW background, whether there's any effect or not. So this memory burden effect is something I do not understand, okay? But it has been proposed that the semi-classical description of PBH evaporation, which is based on a self-similarity, cannot continue forever, okay? Which means that you cannot really compute the lifetime of the black hole just by looking at the formulae that I had shown you earlier, okay? There's going to be a back reaction, okay? And in these papers a couple of years ago, namely Jayadwali, proposed that there's a particular way of understanding, if not being able to calculate exactly, there's a particular way of calculating this back reaction effect onto the PBH by so-called the memory burden effect, okay? And it turns out that, because the semi-classical evaporation formalism breaks down at some point, you need to worry about this back reaction effect. And just the upshot of this whole discussion is that a black hole with, let's say, some mass with memory burden is not equivalent to a black hole which is newly formed. Because here on the left side, you need to worry about the back reaction onto this black hole after it has lost half of its mass. All right? So the two questions that we asked in this paper from last year, just a couple of months ago, is that first of all, what are the imprints of memory burden effect onto the induced GW spectrum? And more importantly, can any non-trivial reheating epoch mimic these signatures? All right? So to answer the first question, we sort of have to incorporate now the rate of change of mass, which is affected now due to the memory burden effect. Remember, this was the canonical expression that I had shown in one of my slides. In the absence of any memory burden effect, which is the semi-classical description. But now in the presence of memory burden effect, after a certain epoch when the black hole loses some fraction of its initial mass, you need to worry about this corrections, contributions, and as a result, any signal that you compute, in particular the induced GW signal, is going to be dependent on the evaporation rate of these PBH. This is what we asked. So the question boils down to that if you look at these two scenarios, when you have an initial PBH mass with a given abundance in the radiation domination, and you take into account this Q1 and N1, which is arising from the memory burden effect, Q is here, N is here, whether this can mimic the same set of signatures for a different PBH with a different abundance in a different reheating history, but for Q equal to 0 and N equal to 0, which means in the absence of memory burden. Okay, so in the sense that if there's a degeneracy between the two effects. So we first computed the spectrum that I had showed you earlier for W equal to 1/3, which means in the radiation domination for different sort of values of W for a given mass and abundance. And at the same time, we also computed the signal for Q not equal to 0 and not equal to 0 in the sense that by taking into account the memory burden. And you find that there's a shift in the spectrum, but it still has this sort of very interesting doubly peaked spectrum. And what we also found is that for some set of parameters, you can actually mimic the second peak of the GW, induced GW, arising from memory burden just by changing the reheating history comparison to radiation. We also found that the first peak cannot be mimicked, but the second peak can be mimicked. Okay? And therefore, we concluded that in these scenarios, when you should be taking into account the memory burden effect, the first peak can actually help you in disentangling the contribution arising from one or the other scenario. Okay, so let me summarize here. Sorry for overshooting. As I discussed, PBH are really interesting candidates for the cold dark matter. They are a very interesting probe of small scale dynamics. Inflation can produce significant PBH. Abundance, they are very interesting observational signatures, induced GW in particular, which can be probed by many of these future experiments. And there are, besides the GWs, there are many other interesting imprints that people have been looking at in order to constrain the dynamics of PBH formation during inflation, for instance. And these could be the evaporation mechanism or the very ultralight PBH, or even more interestingly, this memory burden effect. Lastly, let me just thank the funding agencies for their generous support, and I thank you for your attention.
Thanks a lot. So we have time for one question, because we're a bit late. So Thomas.
I mean, I guess there are certain constraints. Epsilon has to be positive, and the potential will be a mess. It's nothing that you will get from particle physics. You might violate the one's identity or duality, but in principle, I guess this is always possible, no? So
let me just sort of try to answer, and it's like, you can always, in my opinion, you can always find a very contrived model, okay, which will satisfy each and everything, let's say 1,000 extra parameters. But perhaps that's not what you want to do at the end of the day. You want to still stay with the beyond simple single field models, but again, not introducing too many degrees of freedom. Otherwise, you lose the predictability of these models. You can always go to a parameter space where you will predict something. So that's one of the remark I made when I was discussing the model, that you can actually rule out this model Okay, if in future, or at least rule out a large part of the parameter space for this particular model, given the current constraints on NS, and if NS becomes even stronger in future.
To give you an example, I mean, if you would add an R squared term, right, and then go to the Einstein frame, I think this would make the potential flatter to the right, and this would, I guess, lift the spectral index.
Yeah, so
and many people would be okay to do this, no?
Could be. I mean, this equivalence of the two frame is something I don't also understand very completely. But in these scenarios, when you're not introducing any additional coupling with curvature, you don't need to necessarily go to the Einstein frame. You can stay in the frame with wherever you are. You just want to affect the inflationary dynamics. I mean, the necessary ingredient is that you have to go away from slow roll. Which frame you are in, what potential you use is up to you. Okay, but this is the necessary ingredient.
So I have one question and one follow-up comment to what Thomas was saying. Can you go to the slide where you had this phi 6 potential with 1 plus d phi xx square?
Here, right?
Yes.
Yeah.
So you see, Thomas, secretly, this potential can mimic the non-minimal coupling, with the d being the non-minimal coupling here, because the phi is like, so the x is like the phi, right? So if you write, if you take d as a non-minimal coupling, you had this. So we,
in fact, by looking at, I mean, as you correctly guessed, by looking at the form of the potential, you can already see that you have already gone to the Einstein frame, because the potential is rescaled by this non-minimal coupling term. However, the reason behind writing in this particular form, because if you start with a 5 to the power 6 potential in the Jordan frame, people will have serious problems. Okay, but if you write it already in this particular way, you can already see that the potential essentially behaves as a quadratic potential at both large phi and small phi. So in terms of, if you talk to a field theory person about the renormalizability of the theory and all that, in that sense, this seems fine, which means that you can still believe the predictions on the larger scales when you compare with the CMB, because the potential is still quadratic.
So I just have one question, but before this, one ending comment on here. So we actually tried to generate the same potential with standard model Higgs and with Gauss Higgs and with MSSM Higgs, with the A term breaking supersymmetry, and you will get almost same, except because of the RG running of the Higgs and whatever model, particle physics model you take, the coefficients becomes time dependent or field dependent. So here you had the prediction of tensor to scalar ratio 0.05, but if this A, B, and C becomes RG scale dependent, we showed that this could be very, very lower, because here the coefficient A, B, C has
so that's
to be
even better, right?
Yeah, so
that's even better.
So if you generate this from, like, we showed it for 3 scenarios: Gauss Higgs, MSSM Higgs, and standard model Higgs with some RG running with the top coupling, you can get this. So now coming to the question that I have. So regarding the inflection point which you showed, so there we found that, so one thing which we found was that depending upon the velocity at which the field starts to enter the inflection point or the ultraslow region, and the velocity at which it leaves, you might, and in fact some of the regions enters the quantum diffusion region. So there the predictions.
I did not even bring up that word, the stochastic effects or the quantum diffusion. The point is that the dynamics is very much stochastic around the inflection point. Okay, therefore you need to worry about it. And in fact, people have shown, including you, that the outcome, if you take into account the quantum effects, are different than this canonical analysis when you ignore them. So one necessarily has to include the quantum effects around that regime. Absolutely.
And one of the very distinct things that happens is that you not only form the p beach, but they become clusters as well.
Yes.
Because you are producing from the non-Gaussian.
Yes.
Okay, so let's thank Rajeev again.